Hello, hello. Um, okay. So I know last week was a more of a project update and project status related week. Um, the reason why I'm emphasizing project is because it is a big component of your grade, and that's the fun part of this course actually. Not focused on assignments which are too structured, too narrow. You get to choose some topic and explore it. So hopefully you guys are continuing to do that, and we only have very few weeks to the actual project submission. So 29th is the date when you need to submit, because on 30th you'll be discussing your learnings, whatever you did in your project to the rest of the students. I will give information on how to do the presentations. The presentation slides, if you have slides, I'll just set up a box folder so you can just upload it before the class so that it's convenient. So I will send that information right before, like very close to that day. Okay. Folks will obviously be concerned about what to submit. Definitely submit everything. Especially if you have a large data set, just sample it so that we know like what the input output looks like. You can submit a model if there's a model involved. Um, and obviously, if you have notebooks and stuff that relates to training or doing inference, that would be the place. That those are the artifacts that you would submit in addition to your report. Okay. So with that, let me get into the topic for today. So what I thought was, instead of motivating more about reinforcement learning, I'm going to do that during the break because I have some videos and stuff for that. So we'll try to use the first part to really get into some heavy details about reinforcement learning. Okay, so that's the plan. So where are we? So we are in this. I mean, it says lecture 10, but like whatever, the 10th session. So we're going to talk about a few things: policies, state action, value functions, and if possible, we'll try to also try to do Bellman equations and Q learning. Okay, so we'll see how much we can get. It's the same slide deck, lecture 10 and 11 that you can see on the tab there. So what are the goals, right? So last time, as in before last time's project meeting, we were talking about online learning, online machine learning group, and we were trying to differentiate it with respect to supervised learning. And the big idea there is, or at least one of the big ideas there, is binary feedback. Okay, because you're getting just the feedback of what you did and how well that performed, and you don't know what else you could have done and how that would have performed. You have to do what is called exploration. Okay, which exploration is just a fancy word to say you have to do trial and error. You have to try something else to know how well you can do in terms of those other actions. Okay, so that's the big idea. We'll revisit the same idea in our setting. So last time, I'm not going to look at the last time slides, but last time the goals were to understand the online learning loop, where you're really thinking of taking actions. Actions can be even labels if you want to, if you think of a supervised learning setting. But it's just that you take actions given context or no context. And if you had context, like a feature vector, you take actions or predict labels. You get feedback, which is some sort of a reward signal. Okay, which need not be whether the label is correct or not, because that's really high quality information. It's just for a given label, how much money did you make, or how much, how effective was the drug or something. You only get the feedback for the action you took, and based on the feedback, the next interaction or the next time you can deploy your action, you want to improve. Okay, and so we saw two levels of interesting problems: multi-arm advantage, where there was no context, and you just had to figure out between 5 actions which one was a good one. And still that was hard. Okay, that's literally, you could just do round robin, but you would be very inefficient in terms of number of interactions. And there were some better ideas so that you can be a little bit efficient in terms of figuring out which action is the best. Okay, and there were some algorithms, epsilon greedy, UCB that we saw, and EXP3. And then the last thing we saw before, 2 weeks ago, was introduce the idea of a context. Context is nothing but the same as a feature vector. And today's class we'll be talking about something called state. It's the same as a context. Okay, this is just vocabulary in that literature. So contextual bandit is you have a state, and so for under every situation or every context, you want to figure out what's the best action. That's even more harder problem. Like if you thought bandit problem was hard because you have to explore and figure out which action is the actual best best one. Now I can imagine there's so many contexts. It's not like the number of feature vectors are finite, right? So there's not like the only 3 or 4 situations under which you find the best action. Every user is different. So if you think of a user profile, for example, coming in a marketing setting, there could be infinite number of contexts, and you need to figure out what is the best action to take. And that's where the problem kind of becomes complex. Okay, so it looks like a supervised learning problem, except you're getting binary feedback, so you have to deal with that. So today, the goal is we will look at reinforcement learning. Is the same as online machine learning, except your current actions influence future states. We'll look at I'm going to go into details, about all this, whatever I said again, when I use slides. But so the goal by the end of the session, you should be able to appreciate, okay, what is reinforcement learning and how is it different from supervised learning? Okay, it takes some time to kind of differentiate this. It's not, although we spent one lecture on just trying to differentiate supervised learning with bandits and so on, it still takes some time. Okay, this idea of bandit feedback is not, immediate, like especially if you spent a lot of time on supervised learning. So end of the session, hopefully, what is RL? And then we're going to start talking about some setup, right? Just like in supervised learning, we have to talk about, okay, data xi yi pair, the prediction model, some M or some F. There's some setup involved to kind of describe the problem, and okay, here's the objective function, here's the cross entropy loss, and things like that. Similarly, to kind of set the stage for coming up with solutions for RL, like last time we saw epsilon greedy and all that. There's not too much setup because there's no context and stuff, things like that. Here we'll have to set up the problem, like what is there's not going to be a prediction function, but it's going to be some other things. Okay, which the other things are actually in the name of the lecture here. The other things are going to be what are called policies and state action value functions. And so we're going to to kind of state them, we need this notion of what is called a Markov decision process. Okay, it's okay, we'll disambiguate all these 3 words in the lecture, but that's one of the goals by the end of the lesson, to have a understanding of what is Markov decision process, and therefore the third goal is to understand what are these 2 things, policies and value functions. Okay, so that's the goal for today. So if you think of supervised learning, it's very similar to, okay, here's the prediction function, here's the loss function, here's the data xi yi. It's very similar to that. So you need to set something up, right? So that's a goal. If we can get to the next set of goals, I'll talk about it, but let me not cover these goals right now. So I don't want to rush through. So we have 2 sets of lectures, but we only have 1 more session left after this. So we will see how much we cover. Okay, it's not really important to cover everything. It's important to kind of understand at least the basics. Okay, so great. So with that, let's start. So this slide deck number 10 and 11 has the first portion talking about complex decisions. And this is something I've already covered, or at least briefly talked about. Hey, decisions can be complex. They're not a simple mapping from prediction to a decision. I've already talked about it. So I don't want to spend too much time on that. So I'll skip the first bullet point here. Okay. It's just talking about various types of decisions. You can look at it later. I mean, every time, when we start a lecture, we need to motivate like why we're studying even this topic, right? So during the break, I'll show some illustrations, more illustrations actually. But this slide, we've seen it before in the last lecture. It's just showing, I think, about 48 games in a game environment called Atari game environment. These are just 2D games. I don't know if anybody has played these 2D games on a console or a handheld device before. But in 2013, about 10 years ago, the Google DeepMind showed how an agent using those primitives, policies, value functions, whatever, using those primitives, be able to do that exploration, deal with the bad feedback and figure out what actions to take, okay, in an online manner. So it's an online learning problem, okay. So and the same architecture, same whatever the software which uses these policies and value functions and whatnot, but they will play all these games, and in some games it was doing better than some of the really expert humans, okay, in terms of scoring, in terms of scores. Not all games, and we'll actually see what the actual architecture is in a case study next time. Okay, next lecture will really be about what is the what are the details of this breakthrough. And we'll also talk about this breakthrough, which also was something I shared last week or 2 weeks ago, where it's a very deterministic system. It's a board game, so rules are well defined. There's nothing to explore and exploit as such. But still, it's a game where computers found it really hard to play against humans. Even like 6 years ago, they were only able to play up to some level, like a second tier level, and then 6 years ago they started beating the top humans. Okay, so this person was the then number 1 ranked player in this sport, and since then software has taken over and it's way better than humans. It's very similar to the case of chess. I don't know if some of you have played chess. Till the mid 90s, humans were way better than chess, way better than computers in chess. But in late 90s, people were able to come up with programs which can compute very quickly and be able to play chess at a superhuman level. So we'll see this case study, but here it's not really apparent what is the exploration, what is the bandit feedback, but we'll get to that. We'll see how it connects to reinforcement learning data. Okay. So where I want to start with is just show this as in the context of previous lecture, and then really get into the primitives of reinforcement learning, what is reinforcement learning and all that. Just so that when we go through this, if you want to think of the previous problems that we looked at in the last lecture, those previous problems are also reinforcement learning problems. Okay, there is still a reinforcement. What is reinforcement? It's just informally, it's just a way to understand that I'm learning more and more by doing trial and error. I'm getting reinforcement, I'm getting feedback through which I'm reinforcing that, okay, some actions are bad, some actions are good. That's what's happening in the multi-bandit setting. Okay, some actions are good, some actions are bad. I need to collect rewards, so I need to kind of gravitate towards the actions which are paying me more in terms of reward signal. Okay. The same idea. There is also reinforcement learning setting, except now I have the notion of a state or a context. Okay, I'm going to use the word state because that's what's standard in the literature. I take some actions in every state, every context that I'm given, and both the situation or the state and my action determine the reward. For example, if the market is down and I take a buy action on I don't know, IBM or Tesla, I might make some dollars, right? But the interesting thing about that situation is that let's say I did a buy action, about 100 Tesla shares. I did make some money in that period, let's say next day. That has nothing to do with what the state of the market is tomorrow, because I'm such a small player. Okay, so my actions don't influence the state of the market at all, unless I'm a really big, like I'm a really big player, like a big hedge fund or a big asset manager who kind of sold $1 billion of Tesla stock. Then it's going to influence what's going to happen in the future in terms of the market, right? So so that's contextual bandits, right? And this is what we looked at last time, and we really didn't frame it as a reinforcement learning problem, although there is reinforcement because of this bandit feedback. There is exploitation, so there's trial and error. But we pose them as online learning problems. Okay, and we try to say how is the different from supervised learning. Today, we will still try to say how is the different from supervised learning, but it's going to be a more general situation where my actions will influence what's going to happen tomorrow. Okay, or in the next interaction. So this is going to be very crucial. And going back to that Atari game setting, if you think of the one of the games, like depending on what move you made on your joystick now, will influence what screen you see next, right? If you, let's say you're playing Mario or one of these games, then you do a jump, then you know what the next screen should look like. It's going to be dependent on your action. Okay, let's say the screen is the state, then right. So therefore, there's an interesting thing that you can do here, which is in addition to exploration and exploitation, which is like trying out, oh, what actions work well now, which is because you can get a sense of if you try different actions, maybe you get immediate reward. You can also do an interesting thing, which is trade off reward across time, okay, across interactions. That's the new thing, which is that you can try to get low reward now so that maybe you end up in a better state tomorrow or later on where you can reap a lot more reward. Okay. So for example, and this is a little bit of an analogy. For example, you guys spending time here, is boring, right? It's not giving you immediate reward or fun, but by being here, you learn reinforcement learning. Maybe tomorrow in your interview, it's exactly what's asked, and you get the job, right? You make $100,000 or $200,000, right? So I'm just saying that there's a trade-off that you can make, and you can actively make that. That was not there in the previous situation. So you can. It's like, I don't know if you have since we are in the business school, right? Like how to manage cash flow. So you can actually have, you could have a big cash flow in and out event in one time period, or you can spread it out, like think of a loan or something where you're paying off interest. You can spread rewards across time and be in a better situation. So it's like that, okay? So that's the situation we'll look at. So let's come back to the basics. I'll start with, again, what is RL. I'll not try to tie it back again to online machine learning loop that we saw last time. That was the central focus last lecture, last set of slides. But here it's exactly the same, but I'll just use the RL terminologies. Okay. So firstly, decision making. I think last time also I mentioned it's a huge field. There are other courses in the department, revenue management, inventory management, and all that. But within decision making, right, there's one-time decision making and there is sequential decision making. Sequential just means that you're making decisions again and again, and that's what we saw in online machine learning, right? You're taking actions again and again. Within sequential decision making, you might know everything about the situation in which you're needing to make sequences of decisions. Like in the game of Go, you know everything. You know the board, you know the rules, you know everything that is needed to know to make decisions. Okay, so that problem is called a planning problem, a planning situation. It's slightly related, but what we are interested in is sequential decision making, where we don't know how to take best action. That's why we need to explore. Okay, we're getting feedback, we're doing trial and error, we are exploring. Okay, and so that narrow subtopic in decision making is what we're going to look at. Okay, so don't think that reinforcement learning is everything is the everything of decision making field. But it's one interesting direction, and it has intersections with deep learning. Okay, so what are the ingredients, right? So just like in supervised learning, there's going to be an agent. What's the parallel to supervised learning? There's going to be a prediction model. Okay, so this agent is going to hold something like a prediction model here. Okay, the agent is going to make actions. Just think of it this way, right? If the agent had a prediction model, they would spit out labels. Here, the agent will hold something which will spit out actions. Okay. And there's going to be two other things, the environment and feedback signal. Those two are like the data part of this problem. Okay? So in supervised learning, you just have data x and y. So an input feature vector and output label or output prediction. The environment produces your feature vectors, so states. Okay. And the feedback signal is like your, it's not exactly the label, but it could be some reward signal or feedback signal. Right? But this is actually this reward. So these two constitute your data part of the problem, and agent kind of controls actions, which you can think of as like prediction problem. So I'm just trying to map it to, just some analogy to supervised learning. And the third bullet point is just saying that, it's different from contextual management because your actions can influence the future. Okay. So those are the elements, and we'll actually spend some time kind of grounding them a little bit more. Really, the central goal of this type of decision-making problem, when you don't know everything, you're not just planning. When you don't know, you have to do trial and error. Is to how to select actions to maximize total reward. Okay. Even if you know things, which is not going to be reinforcement learning, it's called, as I said, it's called planning problem. There also is the same objective: how to take actions so as to maximize reward. But here we have to do exploration and exploitation, right? Just like in nonlinear machine learning situation. Once you set the problem up this way, okay, there's an agent, there's an environment, there's a feedback signal, then you can talk about, and once you set an appropriate objective, then you can talk about solution strategies. Okay? So let's briefly talk about the environment, which when I said, by which I mean I want to set the notation here a little bit. So let's say the agent takes an action capital AT. I'm going to use capital letters to represent that these could be random variables. Okay. Let's not make the connection to random variables immediately right now. We'll make it later, but I'm going to use consistently like capital letters for random variables. Let's say the action that the agent takes is AT. Okay. And the environment is going to receive that action. So if you think of like if I take an action from the other perspective, the environment sees that action, right? And then seeing that action, the environment will say, okay, now the new situation, because we took an action, is st plus 1. Okay, S stands for state, kind of a proxy for state. So st plus 1 is the new state that the environment generates. It's as if, it's just to kind of abstract it out. The environment generates a new state and also generates this reward thing. That's the data part of your problem. Okay, state and reward. It's very similar to a feature vector and a label. Okay, similar as an analogous, but not really exactly the same. And T indexes time or some ordering, right? You have interactions, multiple times you're taking decisions. So you could take a decision now, you get into a new state and you get some immediate reward. In that new state, you take another action, you get into another state, you get some immediate reward, and so on. You keep getting reward signals, and your objective is to maximize the sum of these reward signals. And you can put an expectation if these are random variables, and you want to kind of maximize the expected reward. One important thing, which will be important later, is this idea of a Markov assumption. Okay, so this assumption is just it's not strictly necessary at this point, but we will see that when we talk about Markov addition processes, the word Markov just corresponds to the fact that given the current state, the future state, st plus 1, these are all just random variables. If you want to really ground it, think of it as like a feature vector. This feature vector, given the current feature vector, is independent of all past feature vectors up to this point. So S1 to ST minus 1 get dropped if ST is already known. Okay. So this is called a Markovian assumption. And we'll come back to this when we talk about Markov addition process again. Okay, but here I just wanted to point this out. Any questions here up to this point? We just introduced one component of this RL problem setting. Okay, one part, which is the environment. Next, we'll talk about agent. Am I too fast, too slow? Good, good pacing. Okay, so what is the agent? As I said, agent is just the person who's taking decisions. Okay, like the decision maker, you can call it, right? How is the person making decisions? Remember, we have to use some, like internally, the person needs to make a decision by using a function which maps from states to actions. Okay, internally, and that's called a policy. But what does the agent do, right? They look at the immediate, they look at the reward, look at the state, and given this new state, they need to make take another action, AT plus 1. Okay. So basically, they're observing these things, these pairs. They look like feature and labels, but they're not, and they are not IID. Okay, because my actions influence future states. So this whole data set is not IID. Okay? So that's another big departure from supervised learning. In supervised learning, if we permute rows of my tabular data, it's still the same data because my objective function is just a sum of these losses per example, and if you change the ordering, it doesn't matter. The agent's objective is to maximize the expected total future reward or total reward collected. Okay, so that's why these rewards are random variables, and some of these rewards want to maximize. Okay, so I take actions at AT plus 1, AT plus 2, and so on. Okay. What is this gamma? We'll get back to this. This is just a discount factor. Okay, gamma is this Greek symbol, is just a scalar between 0 to 1. It's just a discount factor. I discount the future rewards. Okay, I mean those who are in finance, you understand like the time value of money, right? So $1 in the future is less valuable than $1 today. Okay, I mean it can be more valuable, depends, but so that's just time value of money. But in general, actually, it's just to ensure that the summation is going to be finite. Okay? Yeah, and as I said, the last thing which the agent can trade off getting current reward, get less current reward, so that they can end up in better states or better situations, so they can get higher reward later on. That was not a part. That was not something that you would see in the contextual binary setting or the multi-AND binary setting. Okay, every interaction is independent. Any questions? Okay, so reward. There's a lot of like reasoning of how to set this reward up, because it has some other deeper connections. But for us, it's very similar to the contextual binary setting or the multi-AND method. So somebody is giving me, and somebody in the sense, in this case, the environment is giving me a signal, which is what I want to optimize. Like the expected value of these reward numbers is what I want to optimize. It's just a question of why is this is this a constrained setting? Is this a constrained problem definition? Okay, it's not. Turns out that anything, all sorts of goals that you have in decision making, you can actually kind of map it down to maximization of certain expected cumulative. Doesn't have to be expected, but some reward maximization. You can actually map it down to appropriate reward maximization problem. Or in other words, informally, all I'm saying is you can always have some objective function. Okay, so which is numeric, and so you can try to maximize it. Okay. So this statement is just saying there's a reward function signal that you need to kind of track and get more of it. Right, and I guess that's the goal. The goal is to select actions to maximize total future reward. I'm just using the word future, but obviously you can't do anything about the rewards you've already gotten. You kind of have to take action so that you can maximize the rewards you're collecting over time. Okay. And there are a lot of issues. This is just listing actions have long-term consequences, so you need to be cautious about what actions you're taking. And for example, if you're doing self-driving and you turn left and there's nothing else, you can't undo and go back to the previous situation and turn right. So there is a consequence of taking actions. Interestingly, rewards can be delayed. Okay, and this is where in contextual management, every interaction is kind of independent. Your actions don't influence the future state, and so for action you took, whatever you reward you got is kind of immediate. Okay? You don't have to. If you take an action now, it's not like you have to wait a long time before some reward realizes. Okay? Whereas in other sequential decision-making settings, you may have to wait a long time or a variable length of time to kind of realize a reward. Okay, so we'll see these relaxations or this type of patterns coming up later. Okay, maybe in the case studies. Yeah. So let me not go into the examples. So let's look at what the previous 3 slides were talking about. There's an environment, there's an agent, and there's an interaction between them. The environment sends state and the reward from the previous action, and then the agent sends the action AT, looking at this current state. Maybe the reward is also factored into learning, right? So reward is factored into learning. And then given that action, the environment says, okay, hey, given this action, this is your new situation, this is the immediate reward you get, and so on. Okay, so it's just that in contextual binary setting, this action did not influence this. In the current situation, this action can influence this. This action can influence all future states. So, any questions here in terms of the interactivity? So this is literally the for loop with three steps of the for loop. But I don't want to get back to that online machine learning for loop. Let's use this view, this perspective. Okay, one last time to discuss supervised learning. I'm gonna just now stop talking about supervised learning. So the agent, which is supposed to do reinforcement learning, as in the agent is supposed to do exploration, exploitation. The agent is going to maintain maintain that gadget which can predict, which can actually take actions, right? Which can take actions. Just like in supervised learning, this guy is going to maintain a prediction function. It's going to predict labels. So similarly, this guy is going to maintain some gadget. It's called a policy, where it looks very similar to a prediction function. It's going to spit out actions. Okay. Give the actions to the environment. The environment says, okay, hey, this is the action you took. I'm going to give you a reward signal, and I'm going to tell you what future situation you're going to be in. Okay, there is this online loop. Okay. Whereas in supervised machine learning, there is no online loop. Okay. These outputs have nothing to do with what new inputs you get. Okay. Maybe in the real world situation where you're using the supervised learning algorithm, maybe the new inputs get influenced by what actions you took. But it's just that when you're training your prediction model, it doesn't know, right? It just assumes IID data and whatnot. Right? And this thing in the red here is just showing that this feedback is actually what's called full information feedback. This is not banded feedback. Okay, in the sense that if the input is an image, and let's say your output is it's a dog, you actually, if you want to improve your model, you should actually get back the true label for that input image. Okay, not just the answer that okay, it's not a dog. You said a dog. The feedback cannot be it's not a dog. It has to be hey, what is the actual image? Because otherwise you can't use it. Here, let's say input is an image like the screen of that game, and you took an action like a joystick left move. You get a reward. Okay, maybe the score increase or decrease. That's it. It doesn't tell you what the right action should have been. Okay, maybe instead of moving left, you should have moved right, and you could have gotten more reward. Okay, that's not told to you. So you have to do trial and error. Okay. Hopefully, this is clear in terms of the difference between supervised learning and this. Any questions? I mean, I don't know how much you've been exposed to online learning and reinforcement learning, but this is a big departure from supervised learning. Okay, and real world situations, there's going to be feedback loops. But that doesn't mean that you should not be using supervised learning. Okay, you can still use supervised learning as you just know that you are kind of not modeling the reality, correctly, and sometimes you may be, it may be risky to not model it correctly. Otherwise, every tool in your toolkit can be used in situations where the situation is not exactly amenable to your toolkit. It's still okay. Okay. As I said, there's an agent, there's an environment, and there's interaction. Now we're going to talk about how do we now, how does the agent make those actions? Okay, make those because the agent has to report, or take decisions, right? Those actions. So inside the agent has to maintain some objects. Okay, very similar to the supervised learning setting, where the supervised learning gadget has to maintain this prediction function, right? The F hat or whatever you want to call it. Similarly, this agent has to maintain some gadget to make, to suggest those actions. And that gadget or that representation could be a policy, could be a value function, could be a model of the environment, or all three of them. It's not like an if-else situation. So these are the elements with which it can take actions, okay, or report actions or take actions in the environment. Okay. The policy is the most straightforward. Policy is literally given the state, what is my distribution over actions, or what is my action? Okay. A value function is something that is probably the first time you'll be seeing it, unless you've seen it before. It's some sort of scoring of how good a state is. Okay. It's something, something that you've not seen before, but we will spend some time understanding it. It's basically some sort of number associated with each state. Okay. Even if your actions have nothing to do with numbers, so if your action is like move left, move right, that's still okay. But in every state, but internally, the agent can maintain a function which is like how valuable is the state. That's fine, and we'll actually spend some time understanding that. And finally, the agent can have a model of the environment. Okay. Remember here, I don't know anything about the environment. I have to try by taking actions, trial and error, learn which actions are actually good, and take those actions. But a way for the agent to kind of act in an environment is that it can try a few things and collect the data and actually reconstruct what would the environment look like. Like, you could reconstruct oh, the environment can be represented using a system of linear equations. Perhaps, maybe it follows some physics, So model just means a model of the environment. Because if you have a model of the environment, what you can do is, instead of worrying about reinforcement learning, you can worry about just planning on this known model of the environment. Okay. So, I mean, if what I said doesn't make sense, we'll come back to this in a couple of slides. But I just wanted to lay out that the blue box that you saw here, for this guy, for this agent, the blue box is an agent to take actions, has to maintain some functions or equivalent of that. Just like here, you need to maintain a prediction function. So what does this blue box maintain? It could be a policy, it could be a value function, it could be both, or it could be also a model. It could be all three of them. So what's a policy? A policy is a mapping. It's just a function from a state to an action. So this is like the, if you could get away with it, you would just try to maintain this. Okay. And many solution strategies to reinforcement learning just try to maintain this and ignore the other two things that I mentioned, value functions and model. You don't ignore it. Just try to somehow, learn this or track this. Okay. So what is the policy? Policy is just for every state, produce an action. Or for every state, produce a distribution of actions. And if that's the case, we'll represent it using, so this function is, instead of f hat in supervised learning, here the function is represented using the Greek letter pi, okay, instead of f hat. And given the feature vector of the state, it's producing either an action, like a label, or a distribution of action, which is the probability of me taking action little a, if there's a distribution here. Okay? It's just a probability mass function. Okay? So let's say I have, I can move left, I move right, I move forward, those three actions. Then this can be for in my given state, wherever I am. If I can take three actions, then there's going to be a probability mass function with three values which sum up to 1. Okay? That's called a stochastic policy. That's called a deterministic policy. If in the state already the action is hey, take left, right? Then there's no distribution. This is a little bit more general than the previous one. Okay. Actually, we have seen stochastic policies in multi-arm binary setting as well as the contextual binary setting. Okay. When we were doing a distribution over actions, that's literally what this is. This is a distribution of actions. Okay. In EXP4, we did have a distribution over actions. Okay. So that's a policy. And so here's an example of how a policy would look like. So this is just a pictorial example, illustrative example, just to see what an environment is. Because so far I've been talking in abstract in terms of what is an agent, what's an environment, and so on. So let's kind of ground it, and also ground what a policy is. So this picture on the top left is an example two-dimensional environment. Okay. So what is the state in this picture? State is it's basically coordinates of each cell. Okay. Every white box here is like a place where you can go, okay, or you can take actions to go there, and so each white box is a state, and if you take an action, environment will say, hey, here's the new white box you went to. Okay, that's the new SP+1, and you may get a reward. Environment will say only, let's say you reach the goal, maybe the environment will give you $100. Till you reach the goal, the environment keeps giving you $0. Okay, for example. Actually, here the environment gives you -$1 every time till you actually hit the goal. Okay, it's like, okay, get to the goal soon, otherwise I'm going to keep collecting $1 from you, right? So in fact, the agent has 4 actions here: north, east, south, and west. So in every cell, obviously subject to constraints. Here in this cell, for example, you can only go north and south. You can't go left and right. But in some, actually, I don't think there's any cell where you can do all 4. But so those are the actions. Okay, and state is the agent's location, which is that one of these white cells. Okay, so I hope this environment is clear, and what states are is clear, and what rewards are is clear, and what actions are permissible is clear. Okay. If that is clear, then we can talk about an example policy. Okay. We're not doing any optimization We're not figuring out what is the best policy, nothing. I mean, you can probably eyeball what's the right policy to get to the goal. But here's an example policy. In every state, what to do. This is a deterministic policy. It's just saying, hey, if you're in this cell, go south. Right? That's why there's a red arrow going down. If you're in this cell, go west. Right? So this is just an example policy, just an illustration of what a policy means. Just a function from every state, what to do. It could have been stochastic instead of just deterministic saying, hey, go left with 90% probability, go left, or whatever, go east with 10% probability, go somewhere else. Okay. So, any questions here? No? Okay. So now let's talk about something that is new, which is called a value function. Okay. Remember, what we are going through is just what is the policy, what's the value function, and what's the model. Okay. So value function is a what do you want to do? Is we want to kind of track this auxiliary function. It's not a function which can tell me what actions to take at every state, right? Like the policy function's role is literally doing that. It's already for every state what action to take. So what is this function doing? Right? This is a function that is like an auxiliary thing. It's a second thing that you could maintain. Actually, agents could maintain. So solution strategies could maintain, which can then be converted to figure out what action to take. Okay, it's not like this function itself will not tell you what action to take. At least the function is just giving you a score of how good of a state is. So, but there's a way to use this information, use this auxiliary function, or this, I guess, not a policy function, to actually take actions also. Okay, so there's some extra steps you can take, but let's just focus on what is the function, right? The function is basically to kind of representing the goodness or badness of states. Okay, some states are good and some states are bad. Okay, and we'll see that in the same grid example in the next slide. But before goodness and badness, how do I say some states are good and some states are bad? There's a very simple way to do that. Okay, it's just a state is good if the value of the state under a policy, as defined as the expected rewards I can collect starting from that state under that policy, is high. Okay, so what is the value of a state? Is just nothing but given a policy. If I can keep using that policy, I'll keep collecting some rewards. Right? The expectation of that is the value of that state under that policy. And that state is good if the value of that state is high. Okay? State is bad if the value of the state under that policy is low. Okay? And if we can compute this, then there's a way to go and figure out what is the action to take in each state. Okay? But what should be reminiscent of, I mean, what should kind of roughly be a hint here is that this looks pretty close to our objective function. Okay? Remember, the whole point of doing this RL is to actually collect rewards, and hopefully the expectation is as high as possible. Okay, so you can think of, okay, what if now that I know a value for a given policy, if I keep changing policies, I'll get different values that starting from some potentially starting state, then I can figure out what's the best. If I can somehow figure out what's the best policy, then I'll know what the objective of that. I mean, how much rewards I will collect. Okay, so it's kind of very closely connected to the objective of this reinforcement learning problem. Okay, but this is what the value of the state is, and let's actually look at the example of the same board from before. So it's the same situation, 2D grid, which means each cell is a state. Okay, each location is a state, and the actions are still northwest, east, south that you can take one step, and the reward is every step you take, you get a -1 reward. Okay, so recollect, I think you can see that reward is -1 per time. So it doesn't matter where you go. So let's say I was here. If I go west, if I go east or I go south, I actually get a -1 point, immediate reward, -1 point. Okay, so this is the same situation. Here's the visualization of the value function. What is the value function? For every state, give me a number. Okay, so you can see there's a bunch of numbers put in here. All are integers, or mostly because let's assume that the discount the gamma thing is 1 there in the previous slide in the definition, And you can see that there's a nice link, right? So the difference between these two is 1 - 1 units or 1 units, right? The farther you're going away from the goal, you're basically incurring an extra -1, right? So you can see that if you're the right here, right? If your position is here, right? So let's say your agent is here, you just need to take one east action to reach the goal. Let's say the goal is right outside. If you're here, if you take one step, let's say you're at the goal. Because you took one step, you incurred a reward of -1. Okay, so that's the value of being in the state. If you're in the state, you are, at least in relative sense, very good because you only because your value is pretty high related to every other state. In fact, the value is highest compared to every other state. So farther you're getting away from the goal, the value of being in a state is pretty bad. Okay, so it's kind of the value function is kind of telling you, hey, if you're in this time, if you're at the start, your value is -16, it's pretty bad. But if you actually go over here, you're worse than being in the starting point. Okay, so these states are even worse than being in the starting point. Okay, so there's no kind of it's not good to be in these states. Okay, so that's what a value function is. So we'll actually see how it's actually useful in a few slides. But the value of a state is nothing but that cumulate the sum of the expected rewards you can collect from that state under a policy. Okay. Any questions here? No? Yeah. So right now we are not talking about how we're gonna solve this reinforcement learning problem. Okay. Right now that blue box that we saw, I think 2 slides ago, that agent needs to use something to kind of make actions. And what is that something? It could be the policy function that we saw. It could be the value function that we are seeing here. It could be use the model that we're going to see next. But these are just primitives. How the agent is going to figure out and change policies and whatnot, we'll see that later. Okay. Oh, -16 is here and here. That's just so it's the same policy. Actually, there is an underlying policy here. The policy is the one we saw, like the red arrows. That's the policy, right? So if you are in the state, go east. In the state, go north. Okay, that's the policy here. But the policy is completely defined in the state space for these collection of states, right? Under that policy, what is the value of being in that starting state or the below state? Both of them have the same value, -16. That's because whether you're on the starting side or one below, the collection of rewards you get to the goal is the same. I mean, all I'm saying is, if you go from here all the way to the goal, it's -16 points away. Whether you're from here and go all the way to the goal, it's -16 points away. Yeah. Okay, so let's look at the third component, which is, as I said, like reinforcement learning problem. There's a closely associated problem called the planning problem. Okay, the planning problem, everything about the environment is known. What do I mean by that statement? Everything about the environment is known. I just mean that you would know how under every action I go from a state to a state, and how under every action in a given state, what reward I get. If I know these two quantities, then I know everything about the environment, right? If somebody tells me, hey, from every state, if you take from any state, if you take a certain action, the probability of you going to state S prime is given by some number. If this quantity is known for every situation, then I know everything about the environment. I don't have to interact with the environment or try, explore, exploit anything to know what's going to happen. I know that if I'm in some state, I take an action, I would know what the probability of me reaching some other state is. If I know that internally, okay, that's useful for me. Okay? Similarly, if I'm in state S and I take some action, if I know internally that I would get some expected reward, for example, then that's useful information. That's what I mean by a model of the environment. If I know the model, I don't have to do a trial and error with the actual environment because I have a model of it. Of course, the environment doesn't have to exactly follow these rules, okay, then there's a departure from what the model you have in the environment, how it behaves. But in the most ideal case, the environment exactly follows this, then it's perfect. Then you don't even have to do any trial and error. If you know this already, you can just solve the planning problem. Okay, that's just an optimization problem. Figure out what action to do in every state, that without any interaction, without any, you don't have to do any interaction, and then just apply that whatever you solved in every situation that you encounter. Okay, that's called planning, and it's a huge field in itself. So that's where it comes back to that complex decisions. I think the first set of slides I had. So even without the machine learning component, decision making is complicated, right? Because decision making can be, you may have to take multiple decisions. Even if you know everything about the world, taking decisions in sequence could be a hard problem. Okay, that's what I mean by this planning problem can be hard. Like, for example, think of it this way, right? So if you have a fleet of trucks and the supply and demand and requests for loads to be moving from point A to point B and so on, to match that trucks to those loads. Okay, if it's just one shot that trucks go to pick from point A to point B only one time, that's okay. That's just one single shot decisions. But because of the decision, now the trucks are at different locations, and in the next time period, you have to again route the trucks to pick up the next set of loads from point B to C and C to D and so on. If you know all that, and still, if you know all the situations that's going to happen in the future, which means that new request that's going to happen, maybe 10 months into the future, how are you going to, how do you decide to route trucks? It's just not going to be like every period you optimize for trucks independently. Okay, that's going to be a very bad idea. Okay, you would know that, okay, in the first decision, if I move the trucks this way, then the next period, they're going to be potentially far away from the new loads or potentially close to the new loads. That's going to influence my next truck's position and therefore assignment. So that's called a planning problem. Okay? Where even if you know everything, it's going to be hard to do that. But in the RL setting, if you know stuff, if you know the model of the environment, at least you don't have to do exploration because you can just figure out what the best action is. So from the RL perspective, it's easy. But even if you had this, solving for the best action is hard. Okay, so it's all related. Okay. Any questions here of what a model is? So what these script P is just representing this conditional probability of the next state being something, given the current state being something, and I took an action. Something. So that's why these are calculators, and the little letters are the actual values of those random variables that I've realized. Okay. So any questions with the notation? I know it's the first time you're seeing this, but there'll be a few more slides with the same notation. So hopefully I'll repeat what they mean again and again. Okay, let's come back to, let's come back to a grid. I mean, this is a little bit of a simpler grid than the previous couple of illustrations. Here, I'm just trying to show the previous slide had this script P and script R, which is just the what the immediate reward is if I take an action, and what is the next state I get to if I'm in a certain state and take an action, right? So here it's just showing the reward, because we know that in every state, no matter what I do, I'm going to get a reward of -1. And that's what I'm putting a -1 everywhere. Okay, so the reward model is simple. Like if you knew, so that the script R part is simple in this illustration, right? I'm not showing the transition probabilities, but you know that if I'm in the state, if I take a east action, then with 100% probability, I might go east, right? So the new state, which is going to be this one, I'm gonna reach there with 100% probability, right? So I mean, there's not much to illustrate about the transition probability in this example, but we will come back to this transition probability in a couple of another illustration in a couple of slides. But anyway, this section was just trying to prime you that the blue box, the agent, when it has to take actions, it has to play with one of these guys, as in like learn one of these guys. Either it has to directly learn the policy, the pi function, or it has to learn the value function and somehow use that to make decisions, or it has to learn the model and then do planning on that to make decisions. Okay, one of these kind of is that it doesn't have to be that only these three are the only ways to figure out what how the agent can learn and do well in terms of reinforcement learning. But these are the popular ways in which people have figured out solution strategies for the reinforcement learning problem. Okay, we aren't talking about solutions yet, but we'll see only one solution in this course, which is called Q learning, at least in detail. There are hundreds of solutions for this problem once you understand what the problem is, okay? Which is this interactivity, maximizing expected reward, and actions having long-term consequences. So you can trade off things by doing, taking certain strategic actions now so that you can actually be better off later. Okay, so if there are no questions, then I'm going to introduce the Markov decision process framework. Okay? It's just a language to kind of formalize what we saw before: the policy, the value function, and the model. In fact, relate them. Okay, they're not like completely unrelated things. They're actually very closely related to each other. Okay, and if we can do that, then we can talk about one solution strategy, which is called Q learning. Okay, and so that's going to be unlike contextual bandits. Contextual bandits, we only saw one solution, EXP4, which is actually not even scalable, by the way. It's not like a good solution, but it is an initial solution. For multi-arm bandits, we saw multiple solution strategies: epsilon greedy, UCB, EXP3, but 3 solutions. Right? Okay. So as we are making the problem more interesting or more general, we're only looking at trying to kind of restrict ourselves to one solution approach. Although in the literature, you'll find many solution approaches. Okay. Okay, so as I said, we'll revisit these 3 components formally. Formally just means that we'll have the mathematical relations between them. Okay, so that if you know one component, how is it related to the other component, we will be able to kind of at least intuitively appreciate how they're related. So as I said, policy is a function given a state is a distribution over actions. Okay, decisions you want to make. Value function for every state under a given policy assigns a number, okay, numeric value to the state. Okay. So every state is going to be a number. Doesn't matter what the actions are. And model is basically 2 objects. This reward object is nothing but for every state, if you take a certain action, what's the immediate reward you can get, immediate expected reward you can get. That's this. Okay. And this is saying in every state little s, if you take an action little a, what's the probability with which you will get to the next state s prime. Okay, that's why 3 subscript, but just I hope this is not, this is a minimum notation, you can't really reduce it further. But these are the 3 things, and we'll try to relate them with each other. Okay, and this relation is one way to do it using what is called Markov decision processes. And we'll actually see, we'll not directly jump to this, we'll also slowly build it up. But this is the framework we want to get to. Because given the framework, it's going to be easy to talk about the planning problem, which is not that important for us for this course, but we can easily also talk about the reinforcement learning problem. Okay, and therefore the solution strategies, which is this. Okay, then we'll address the question of actually optimizing for the best policy and like taking good actions. Okay, so how are you going to set this up, right? How are you going to actually understand what is this Markov decision process? It has pretty heavy words: Markov decision process. So we're going to do that in like 3 steps. Okay. The objective is, why are we even learning Markov decision process? They're a useful way to describe the RL problem. Like when we set up supervised learning problem, we just write down F hats and loss functions and stuff. So here, it's kind of serve the same purpose. And the way we'll kind of understand what a Markov decision process is to start with something simpler, which is called a Markov chain. Okay. And I'll explain all these things in the next slide. We'll start with something called a Markov chain. So there's not going to be any decisions, but we'll already, by just describing the Markov chain, we'll understand what is Markov, what is the process. Okay. And then we'll add rewards. Then we'll get what is called a Markov reward process. And then we'll add actions, and that will lead us to Markov decision process. So there is some kind of a building up that we're going to do. So take a baby step, add something, and then we'll actually get the Markov decision process definition. Okay. So let's start with the Markov chain. I don't know if you have have you guys heard of Gibbs sampling? Nobody? In 575, did Professor Lee cover Gibbs sampling? Don't remember. No. Okay, no Gibbs sampling. Have you heard of Monte Carlo Markov chain? MCMC? No, you have heard of it. Okay. I mean, at least you heard the acronym. Doesn't matter if you don't know what the details are. It's okay. Okay, so let's actually start with what is the Markov chain or Markov process. So by the way, chain and process, these are interchangeable. And the word process, it's not related to process engineering in chemical engineering. So process just means a sequence of random variables, okay? A collection of random variables. Okay? A chain just means a collection of random variables. Okay, processes. If you've heard of the word stochastic process, there are courses in other departments on stochastic processes. Processes are just a collection of random variables. Okay. So Markov chain or Markov process is just talking about a property that this collection of random variables satisfy, which is just the Markovian property. What is the property? The property of the new state or the next random variable, let's say, taking a value s prime, is only influenced by what the previous random variable's value is, and not all the other random variables that took values before it. Okay? This Markov property, we have seen it, I think, in the second and third slide. Basically, given the value of one of the random variables, all the previous indexed random variables are irrelevant. Their values are irrelevant to the next random variable taking a specific value. So the next random variable taking a specific value is only dependent on the current random variable taking a specific value. I'm using the word next and current just to represent t plus 1 and t. Okay. So if you have a collection of random variables, you should index it with something, right? So I'm indexing it by the letter t, okay, just to kind of signify maybe perhaps time. So that's the collection of random variables. And we're just saying that the relation between these random variables is such that they are not independent, okay? They're not independent. I mean, they need not be independent. They could be independent, right? Like the value that one of the random variable takes has nothing to do with any other random variable taking any values. For example, think of a coin flipping, right? The previous times I landed heads has nothing to do with the next time if I land heads or tails. For example, that would be an independent collection of random variables. They're not going to be Markovian processes. They're going to be independent processes. Okay, process. But the Markovian version is just that if at all there is dependence, the dependence is only one step. Okay? If at all there is a dependence, there's only one step. Okay? So only the previous realization influences the next realization, but not all the previous realizations. That's Markovian property. And what we are looking at is what is called time homogeneous Markov chains, discrete Markov chains. Discrete means there is a discrete time index, like t is equal to 10, and this is t is equal to 11, and so on. So we are in it's called discrete time indexing. And time homogeneous just means that this conditional probability here doesn't change if this t becomes t plus 2 and this t becomes t plus 3. Okay? In the sense that the way st plus 1 and st are related to each other is the same as s1 and s0 is related to each other, and the same as s10 and s9 are related to each other. So there's the same kind of conditional effect going on, and that's why we can get in with just one matrix, irrespective of how many such random variables there are. Okay, there could be 1,000,000, there could be 100, but we just need to know what's the probability of going, the next random variable taking some value, given the previous random variable taking some other value. So if let's say each of these random variables is kind of has the same support, as in they're taking the same set of values. Let's say there are little n number of such values. Then this matrix, this can be represented as a matrix which is of the size n cross n. Okay, this is called a stochastic matrix whose row sum is equal to 1, because it's basically capturing if your current state value is 1. Then there's some probability with which you'll go to next state will take the value 1. Some probability the next state will take the value 2. Some probability the next state will take value 3. And some probability the next state will take value n. Okay. So given 1, it has to take one of these n values. So some of those values is going to be 1, right? So row sum is 1. So it's called a stochastic matrix or a transition matrix. Okay. I hope this is something that you've seen before. If not, that's still okay. There's nothing complex going on here. So this is all there is for a Markov chain. Okay. Another important thing is that if you have a Markov chain, there's no decisions to make. You just observe the chain keeps random variables keep taking values based on the previous random variables, and it's just a completely autonomous thing. Okay, so no decisions to make. So here's an example, right? Class 1, class 2, class 3, pass, Facebook, pub, sleep, these are states. Okay. These are all states, just mean these are the values that the random variables can take. Okay. These are the values that random variables can take. So you can start with any place. Let's say you start with class 1. Then according to that, we actually have a matrix, the script P matrix, which essentially follows this idea, right? So if you are st is equal to class 1, then st plus 1 is either Facebook or class 2. Okay, because with 0.5 probability I can enter st plus 1 as class 2, or with 0.5 probability I can be Facebook. Let's say I'm at Facebook, then with 0.9 probability I'll continue to be next state is going to be Facebook, or with 1.1 probability I'll come back to class 1. Okay? And so on. So why is this f squared here? Is because this is what's called an absorbing state. Okay, and if you reach that state, it's like you're 100% gonna be sleeping. Okay, let's say this is for a single day. Okay, so that's where the whole thing ends. So that's the chain. That's the Markov chain. In the sense that it's completely autonomous. In the sense that there's no intervention. So if you're in some state, it's some probability will go somewhere, some other probability will go somewhere else. Okay. Here's a bunch of realizations. Okay, what are called episodes. Okay, the word episode is going to be useful for us later. Here's a bunch of episodes, which means a bunch of realized values of these random variables, starting from a fixed state C1. C1 is just stands for class 1. Okay, I didn't want to write class 1 there. Okay, so you could go C1, C2, C3, pass and sleep. You could go to C1, Facebook, class 1, class 2, sleep, and so on. Okay, so it's just a collection of realizations of these random variables. Okay, so this is actually just considered data. So if you did not know the transition properties, if you observe this collection of realizations, you should be able to do maximum likelihood estimation and figure out what the transition probability matrix is, the matrix that we're talking about. Okay. And instead of looking at, I mean, that's what the data part, but that's one angle to it. But if you want to go back to that model, Markov chain model definition, it's only pretty much driven by one parameter object, which is just the transition probability matrix. And also sometimes you also want to say the starting distribution. Where do you start in that chain? Let's say we always start from class 1. Then this is exactly what the diagram represents. If you're in class 1, 0.5 probability class 2, 0.5 probability Facebook. So the row sum is 1. Okay. Or if you're in pub, 0.2, 0.4, 0.4, the row sum is 1. Right? So this is what a Markov chain is. Any questions? No? Where are we? Okay. So now let's talk about Markov chain with rewards. Okay, it's actually exactly the same as Markov chain, but as the chain is like as the random variables are getting realized one after the other. Okay, by the way, the random variables need to get realized one after the other because the high index random variable is dependent on the previous random variable's value. Like st plus 1 is dependent on st's value. You can't realize the value of st plus 1 without knowing what the value of st is. Okay, so either you can, but let's keep it simple. So you need to have you can only realize the random variables in one order. Okay, so there is some sequentiality there. But Markov reward process anyway is just exactly the same as Markov chain, but has an extra random variable that gets realized. Realize just means just kind of see the value of that random, that extra collection of random variables as a byproduct. Okay, so here is a formal definition. It's just a Markov reward process is a tuple just means a collection, right? We have seen tuples in Python, so it's a collection of states. The transition probability matrix. These two are exactly the same as it's basically defined the Markov chain, and a reward function script R, and a discount factor gamma. This is the same as the time value of discounting. So just think of gamma as 0.9. I mean, this is kind of inconsequential. It's not super important for us, but just we want to tag it along. Okay, so this is the new part. The part in the red is the new stuff. Okay, so script S is just the collection of states, so which is the values that these random variables can take. Script P is that transition matrix, which you just said, okay, what's the probability of being in S prime if your previous state was value S, right? The new stuff is a reward function, which is the expected value of the reward random variable if I'm in a state S. Okay. So if I'm in state S, it's like somebody is flipping a coin, and if the coin falls heads, then they give you $1. The coin falls tails, maybe they give you $0. Okay, it's just saying what is the expected value of that. Okay? Maybe it's a fair coin, then the expected value is going to be $0.5. If you're in that state, the value is $0.5. Okay, it's a number that gets spit out. Okay, and gamma is the discount factor. That's if you recollect, it's just if you want to sum these things, and if the Markov chain, for example, doesn't have an absorbing state, doesn't have that square thing, then you keep going around. It's not going to stop, right? Because you keep every random variable, you can always go to another random variable. You can always go to another random variable. You can always go to another random variable. And so to keep the summation of these expected reward values finite, you can put a discount factor 0.9, because 0.9 or something less than 1, because if you have numbers which are bounded, okay, which means that let's say the numbers only take values between 1 and 10, rewards are only between 1 and 10. Okay, if that's always guaranteed, then no matter how many such numbers you add, as long as you put a discount factor of gamma every time you add these numbers, then those numbers will never sum to any infinite quantity. Okay, this is just the basic sequences and series ideas from, I don't know, calculus. What is it? From some class, right? So let's come back to, yeah. So let's come back to that illustration again. I'll go to that Facebook type, whatever, the class sequence again. But before that, I just wanted to quickly mention a new random variable. It's just a derived random variable in the sense that that random variable is just defined in terms of other random variables. That's what a derived random variable is. So it's called the return random variable, and it's going to be super important. Super important in the sense that it's an interesting quantity. Actually, it's going to help us define value functions later. But anyway, return random variable is nothing but, that's called capital GT. It's a random variable, which is just a sum of other random variables. So in fact, it's a sum of all these reward random variables with some discount factor. This is the time value discount. Okay, so if you want to kind of write it in a shorthand notation, you can use this capital Greek letter sigma. K is equal to 0 to infinity of gamma to the power k. K is like the integer 0, 1, 2, 3, and so on. And then r of t plus k and so on. So this is just a shorthand for that. This return random variable immediately gives us a value function definition, even for a Markov reward process or a Markov chain with rewards. Okay, what is the value function? The value function gives the long-term value of the state little s, state value little s. Okay. What is it? It's nothing but the expectation of the return random variable given the starting from the state st is equal to little s. Okay, that's the definition. So if there are no decisions, no actions to take, the moment you have Markov chain, it's just autonomously like taking values one after the other, right? The moment you have added rewards, you can talk about tallying those rewards, which is this summing up. So that would be called a return random variable. And then you take the expectation of that random variable. You can define that to be the value of being in that state S. Okay, so let's say we're always starting from, let's say we're keeping track from state ST, okay, capital ST. So if it starts from little s, then there's going to be a bunch of such rewards that we collect, right? And if I start with some other state, like S prime, there are potentially different rewards that I'll collect. The expectation of all those realizations, reward realization, is going to be the value of being in that state. Okay. So MRP just stands for Markov reward principle. So even without decisions, you can talk about a value of being in some state. Okay. Any questions here? Yeah.
I don't think this is a question, just a clarification that the reward function is fixed in every single.
So capital RT here, these are random variables. The reward function that you saw in the previous definition is the expectation. Okay. This script RS is the expectation of these random variables. This random variable, which gets emitted given in this state. So this is fixed in the sense that this the expectation is that is not a random, not a random quantity. Okay. So this is fixed, but the individual these capital letters, they can take, there's a random variable, so they can take values, different values. Okay. But to define a Markov reward process, you just need here we're just using the mean values, which are fixed, which are not stochastic. Okay, let's actually look at the example so that we ground things here a little bit. So Markov reward process is the same Markov chain as before. Now what's being added is the things in the red. Okay, these are rewards. Instead of making them stochastic, we just forget about making it stochastic. Let's just give it deterministic. Okay, which means that for example, remember in every state I could have had a reward random variable. Instead of having that random variable, if the random variable takes exactly one value, then kind of a degenerate random variable is taking the same thing. So let's say in every state there's a corresponding associated reward. Okay, the random variable is degenerate, so the expectation is the same as the random variable itself. Okay, so it's just taking the same value all the time. So the support is just one. Is what I'm trying to say. So every state, the circular thing, you have a reward. Okay, doesn't matter what the action is. Sorry, no, there's no action. Sorry, let me back up. So in every state, instead of a reward random variable, you have a fixed reward, and that's it. That's the extra thing that is coming out, like from a Markov chain to a Markov reward process. In this illustration, the only thing that changes is every time you hit a state, you get a number that you can accumulate. Okay. And this state, as I said, is an absorbing state in the sense that once you reach a state, you kind of sleep till the end of the day. Okay, so this is just a slight change from the Markov chain with the extra red numbers. And now you can start talking about return random variables and their expectations. Okay, so what's the value of being in state class 1? Okay, what's the value of being in state class 2? What's the value of being state class 3? Okay, so I don't know if it's confusing to you guys, but I do want to quickly point out that these circular things are the values of the states. Okay, so this S1 could be class 1, but S5 can also be class 1. Okay, so the S1, S2, S3, S4 are the random variables, and the values they take are these circular things on one square. Okay, so what we are seeing is actually if you're in this value, what's the probability of the next state taking another value? Okay, so these are this collection of values. So there are only 7 potential state values here. Okay, 7 cross 7 matrix, if at all you want to think about it that way. So let's say we start from all this class 1, and let's say our discount factor is 1/2. Okay, recall that our return random variable is just going to be the sum of rewards that we can get, starting from one of the states. We have to specify which state. So let's say S1 is equal to class 1. We already fixed that state. So this is the return of being in class 1. Okay, this is the return random variable that is the sum of all these rewards that you can get being in class 1. Okay, this is a completely autonomous thing. So as long as you're in class 1, the Markov chain is autonomously gonna keep realizing random variables. You keep collecting these numbers. There's gammas here so that this sum doesn't blow up basically. And so here are some examples, right? So if you're in class 1, one of the realizations, one of the trajectories, one of the episodes can be class 1 to class 2 to class 3, pass and sleep. Okay, if that's the case, then you can tally what the realization of the return random variable is. It's going to be -2 because in class 1 times -2 because in class 2 with the additional factor of gamma times again -2 with 1/2 to the power 2 That's why it's 1/4. Plus 10 times 1/8 because you pass, so you got a value of 10, but it's 1/2 to the power 3. Okay, that's why there's 1/8. Okay. Similarly, you can have other trajectories, other episodes, other realization sequence of realizations. Okay. And those sums just add up to these. Okay, so let's say the one realization you had a return run variable value to be minus 2.25 and so on. The average of this is the value of being in state class 1 at the beginning. The expectation of these sums is what the value of being in that state class 1 is. Okay. So being in state class 1 has a value of -3. If you are in pub, there could be a different, there will be different summation, so there will be a different value for that. Okay, so an interesting property that is very useful, and it actually underlies Q learning and all the innovation from 2013 that we saw. Like it's a very interesting observation. Okay, it's a nice trick. Is that the value function can be decomposed in two parts, is what they're saying. But basically, the value function at a given state can be related to value functions in other states. Okay, that's what we want. That's what I want to point out. Okay. Which is what this is saying. It's saying that the value function in a given state can be written in terms of the immediate reward and the value of some other state. Okay. So it's saying successor state with some discount factor. But all we're trying to say is that the value. So forget about these 4 equations, but just focus on the left-hand side. The value of being in some state little less has something to do with the value of being in some other state. Instead of little less, it could be S prime here, for example. Okay, so values of different states are related to each other. That's the point of this slide. Obviously, there's some extra algebra going on there, but it's just the core idea is that hey, if the value of a state is high, there's going to be some other states which led to this value being high. Okay? Or if the value of the state is low, there are potentially other states which led to potentially having this value low. Okay. So how do we see that? It's actually very simple because this straightforward at least is because its value of a state is just the expectation of a bunch of random variables. Okay. Expectation of return random variable, obviously, but return random variable is just a bunch of random variables, right? It's just a sum of these capital R random variables with some discounting factors, but don't worry about it, just fixed numbers there. Right? And we know that expectation of a sum of random variables, expectation is a linear operator. Okay. So you can actually interchange, like you can do sums before expectations and so on. So what we're doing from step, this equation to the next step is we're bringing gamma common. And so we're writing this RT plus 2 plus gamma RT plus 3, like because there's a gamma square here, this becomes a gamma here, and so on. Okay. Now this summation here, okay, inside the bracket is actually GT plus 1. It's a return random variable from the next time step onwards. Okay. And then we can see that there's an expectation of 2 random variables here. A part of the expectation can go in here. Okay. If you take the expectation of GT plus 1, that's B of the value of being in state capital ST plus 1. Okay. Okay, so taking a part of the expectation here, you get the value instead of the return random variable. Okay. And so this expectation, the only remaining expectation is, hey, what's going to be the immediate reward? What's going to be the next state? That's it. Whereas this expectation here has to capture, hey, what's the next reward? What's the reward after that? What's the reward after that? What's the reward after that? So, it's basically just using expectation, part of the expectation inside so that you can average it out. And that's why you get the value of some other states here. Okay. So this is a key result which helps with the planning problem. Okay, I keep telling about the planning problem. There's a planning problem, there's a reinforcement learning problem. The planning problem can actually realize on this type of a recursive relation. In fact, we are only at the Markov reward process, but once you get to Markov decision process, this equation is called the Bellman expectation equation. Okay, it's a very, very important result that leads to helping you solve this planning problem efficiently. People who are in computer science, there's this idea called dynamic programming, which is, it's a fancy name. It just means that if you can solve sub problems efficiently, then you can actually bubble these partial solutions to kind of solve the bigger problem. That's actually one incarnation of that is actually this, that value of being in some state is related to value of being in some other states. Actually, you will not probably see this here unless you have kind of spent a ton of time on dynamic programming and so on, but it's actually related. Okay. So let me wrap the Markov reward process and then we can quickly take a break. So there's no new material here. All the equation that we saw at the previous slide is just this value of being in a state is related to the expectation of the reward that I can get in the current state, which is RT plus 1, plus the value of being in the future state that I'll get to. Okay? There is some randomness in the future state I'll get to, because in the current state, there's a probability of going to S prime, there's a probability of going to S double prime, and so on. There's some randomness. But whichever, let's say there are let's say there are two potential random states potential future states I can get to, then there's going to be two such values that are related to the value of the current state. Okay. So let's say I'm in the current state. So this diagram is just showing if you're in the current state, okay, this is just a very illustrated thing, but let's say there's a current state, there's some value, okay. From that state, I can go either to state S prime or maybe some other state S double prime, okay. There's some immediate reward to be collected. If I go to S prime, there's an immediate reward. I'll collect maybe the same reward. Okay? It doesn't matter what the next state is, right? In the Markov reward process, right? Then V of S is equal to R, little r, plus the probability with which I'll get to S prime times the V of S prime, plus the probability I'll get to S double prime times the V of S double prime. That's what the equation of first line is showing. Okay? And that actually, this equation of first line is exactly the equation of second line, because expectation of RT plus 1 is crypt RS. Remember in the definition of Markov reward process, and the expectation of gamma V is nothing but gamma is just a constant. Expectation is nothing but the sum over the probabilities that I'll go to the next state, S prime, times the value of that S prime. Okay. So actually this equation makes it very clear that the value of a state is related to value of other states. Okay. And in fact, the relation is linear. Okay. So you can think of it as a system of equations where there's a linear relationship between values of states. Yeah. That's a powerful idea here. Okay, so we'll not look at Markov addition process before a break. So let's take a break now, and let's resume at 5:10. I wanted to show you since we already know states, actions, and environment and stuff. I wanted to show a script where I want to set up an environment and show what a random agent does and an agent which actually learns will do, but we will do that next time. It's a short script to kind of show how you code it up, just like you've seen it for CNNs and others. Okay, but we'll do that next time. So let's talk about Markov decision process. As I said, we are trying to do a 3-step learning here. We wanted to learn Markov decision process from the get-go, but for that we started with the Markov chain. There's no decisions, no rewards. Then we talked about Markov reward process, where we added rewards, okay, which are still, there's not, they're just being extra random variables that are getting realized. And now we're introducing actions. Okay, now things become non-autonomous. Okay, so because you are intervening, you are saying, okay, hey, take this action. That's influencing the trajectory of the realization of the next random variables. Okay, that's what's the core essential, one of the core essential properties of reinforcement learning. Your actions are influencing the future, not just the rewards, the future states. Okay, so what is the Markov decision process? It's just a Markov reward process, but with decisions. The decisions are just actions. So the only thing that we changed from the previous setup is the things in red. Okay, so therefore in the tuple, we initially had for Markov chain just a state and the transition probability matrix. For Markov reward process, we have state transition probability matrix, reward function, and the discount factor. And now we have another set, so another object, which is the bunch of actions. Okay, let's say it's the same actions everywhere. So to keep it simple, so we have a bunch of actions. Okay, so script A is a set of finite set of actions, and so now our transition property is no more like a matrix, because there's a condition on two things. It's like a tensor. Okay, what is the current state? What's the current action? Under the current state, if you took a certain action, then you get to some new state. Okay, but if you took some other action, maybe you get the same state, or you could get to some other state because of your action. Okay, so your action also influences what the next state you get into. That's why there's a triple indexing here, and I don't think you can reduce beyond that. And similarly, the reward is not just a function of the current state, which is what in the previous illustration we saw, the Facebook class 1 class 2 illustration. It also depends on now actions. Okay, so that's the only, those are the two changes. Okay, we introduced actions, so now the state transitions and the rewards are dependent on the current action. Okay, now let's come back to our illustration. Now this illustration is a little bit different from the previous two illustrations. Okay, let's not map it to the previous illustrations. Here, these states don't have names anymore. Okay? Our actions are going to be to study or to do something else. Either we study, or we do Facebook, or we study or sleep, or we study or go to pub. So now these have become actions. The things in red have become actions. Okay, previously it was something else. So don't connect it to those previous two illustrations. And then for every action, there's also a for every action there's a transition to a next state. Okay. So here in this illustration, it's very simple. So every time you make an action, there's no randomness in which next state you go to. You always put that a very obvious next state. Okay, and you also are tagged along with the reward value as well. Okay, so it resembles our previous illustration a little bit, but let's not make connection. So these blank ones are actually the state values, and we don't give them any names. Let's call it 1, 2, and 3, 4 if you want to. Let's say in those states, if I study, if I take the study action from this state, then I get a reward of +10 and I reach here. If I take a study action from this state, I get a reward of -2 and I reach this state. Okay. So what is this? What is this thing in square box? It's like once you reach this state value, the episode terminates. Yeah, as in like there's nothing else, no more actions to take. Okay. And what is this black thing here? And basically kind of is a state like very similar to the white thing, except you don't get to take any action. I mean, in the sense that it doesn't matter what action you take, with some probability it will go somewhere, with some other probability it will go somewhere, with some probability it will go somewhere. Okay. It's like, you have some action, but it has no effect, if you want to call it that. But if you don't want that distinction, you can think of all these as circles. No, doesn't matter. Okay, so now that we have Markov addition process, now we can introduce the policy. Because previously with Markov chains and Markov reward process, there's no policy. It's an autonomous thing. There's no actions. Okay. Now, what is the policy? Policy is a distribution of actions given a state. Okay. So this is just a function, right? Very similar to our prediction function. In a supervised learning, given every feature vector, you could have a distribution over classes or distribution over labels, right? It's very similar to that. Okay. So that's what we call a policy, a distribution over actions given a state, and therefore it's a function over states. Okay. A policy fully defines the behavior of an agent. Okay. So an agent, if it wants to do trial and error, reinforcement learn, figure out, it can just work with the policy and ignore these value functions and models and so on. Okay, it can do that. Okay. So there are some solution strategies which just focus on policies. Now, quick point is which is not new, is that a Markov addition process is a Markov reward process for a fixed policy. Okay, this is something that is should be also straightforward. Basically, what I'm trying to say is that if there's an MVP like this. Okay. And there is a policy pi. Then under that fixed policy pi, once I fix the policy, there's no further actions to take because the policy is already telling me what actions to take. Okay, which means that the whole thing is autonomous. Okay, and it's spitting out rewards, which means that it's just a Markov reward process. Okay, and the Markov reward process, you can think of script p, script s and script p to the with a superscript of pi. It just means that under that policy there is some Markov reward process. As in the Markov chain is some rewards getting emitted. Okay. So this is, basically what I'm saying is if you have a Markov chain, it's a Markov decision process with a policy pi, that becomes a Markov reward process with some transition probability and with some reward function. That's it. Okay. The reason why I'm saying this is because remember when we were talking about Markov reward process, we had defined value function v of s. Now under the fixed policy, it's a Markov reward process, therefore there is also a value function. Okay. That means that that value function under a fixed policy is exactly the same, okay, as what we discussed before. Okay. So I don't want to drown you guys in a notation, but there is some relation between the MDP's transition probability, I guess, function and the Markov reward process's transition probability matrix. Okay. There's some relation. It's just some averaging effect here, but let's not focus on that too much. Okay, so obviously under a policy, therefore the policy function comes into the picture. Okay, it's nothing complicated, but I don't want to spell it out. It's too much notation there. So because of the previous fact that under a fixed policy, Markov decision process is the same as the Markov reward process, we can talk about value functions again. Exactly the same as before, as in same as the Markov reward process situation, except now we are talking about, since we have fixed policy, we can explicitly state that, okay, this is under this policy pi. Okay. Under the fixed policy pi, there's a value of being in some state, little less, and that's expectation over pi of the return random variable starting from that state little less. Okay, so exactly the same as before, and this with subscript pi there, because under those subscript pi's, as in a fixed policy, is exactly a Markov reward process. Right. So that's called the state value function. But I want to also introduce is another value function called the action value function. Okay. Note that this is, I'm giving you many definitions. So this is going to be the last one, so that we can talk about one solution strategy. Okay, which is called Q learning, and that's why this action value function has this notation Q. Okay. We're almost there. Okay, so don't get bogged down by too much notation. So action value functions is I wanted to introduce it here because this is very related to the state value function that we've been discussing for some time now. State value function is just the expectation of it's the expectation of the return random variable, which is the sum of all rewards that I can get starting from the state little less. The action value function, or also called the state action value function, is exactly the same as this, except it has one extra argument, little a, which means that it's just saying, okay, the action value function is the expectation of the reward, of the return random variable, starting from some state s, taking an action a, and then following the policy. Okay, it's just leaving you the wiggle room for the first action to be something else. Okay. Here, the first action has to be pi of s, because the first action, I'm starting from state s, so my first action has to be pi of s. Okay. Whereas here, my first action is not pi of s, it's some a. Okay. That's why that's an extra degree of freedom. So I'm just saying, first action, I'll let you choose something, and then after that, you keep following the policy. Whatever is the expectation of that return random variable, that's the state action value of that state. Okay, that's what the state action value function is. Why do you need that wiggle room? This is exactly the type of wiggle room you need to explore and exploit. You have to kind of you can't just if you just have this, there's no no control on an explicit action, right? Because pi is already saying what actions take in every state. So there's no explicit thing that you can control. Here you're just tracking one part out and saying, hey, I can make this something free so that I can actually do trial and error with, and let's say leave the in the future, if I have some estimated pi, let's just follow that pi. Okay, so this is pretty much the definitions, and I want to, I want to kind of just relate these two guys. Okay, I'll relate these two guys in a second, but I want to relate them to other value functions. Okay, by which I mean we have already seen this before. The state value, so we have seen this type of an expression before. The value of being in the state is related to the value of being in other states. It's in fact linearly related, okay, because expectation is a linear operator, and that's why this is called a linear equation. Okay, so if you remember, expectation is nothing but sum over probabilities, right? So it's just a bunch of sums. Okay, that's what linearity is. So value of being in a state is related to another bunch of states. So that's just for the state value function. For the action value function, or also called the state action value function, the same idea holds in the sense that the value of being in a state S and taking an action little a is actually related to the value of being in other states and taking other actions. Okay, it's just very similar to analogous. You can actually write check why it works, but it's again the same idea. It's just linearity of expectations. Otherwise, if you remember, there was this return random variable definition here. You just expand it out and take expectations appropriately, you'll get this. Same thing here. Okay. So, and this picture is something that we saw for the value function before, but here we'll see it for the state or the action value function. So all I'm saying is the action value for a state action pair is related to the action value function at some other state action pair. How is it related? By just linearly. So think of this as, let's say this is 10. This is related to some other number, some other state action pair, so some other value, maybe 15. How is it related? Just through these, how is it related? Linearly, and through these transition probability values and reward values. Okay, and these exactly are the model parameters. Okay. I didn't explicitly point this out, and in fact, this is the first time we kind of dropped the expectation notation and explicitly writing down the reward function and the probability function. Okay, so now we have actually related many things, at least two things: value functions and the model. Okay, they are related. Right? This is a value function at some locations or some input values, and the model values at a few locations, a few pairs, right? Yeah.
So in the previous slide, in the original Bellman expectation equation,
yeah,
the one without the action, how do you know what the value for next state is?
Value for the next state.
The one without action.
Yeah. So this here is a random variable, right?
Yeah, but then how
Yeah, that's what. So what? So this equation, this is not a random variable. Okay. This expectation is over the only two remaining things which are random. From this state, what's the reward I'm going to get? This is random, and that's why this expectation is there. And from the state, what's the next state I'm going to go? And that's random. Okay. Those are the only two things that are random. And how do I know that? Is through the state transition probability function, right? Basically, the reason why there's a v here and stuff instead of running sum of rt plus 2 and all that is because the remaining randomness has been averaged out, and that's why I could substitute a v here, because v is an average, is an expectation of something. So all these other random variables somehow became a v at a new state value. Okay, it's just that the state value is not known. Okay, and we wrote a more interpretable expression last time, which I don't want to kind of go there, but the expression was very similar to this. Okay, so this expression explicitly tells you, right, if you are in some state an action, there's an immediate expected reward that you can get, and because you are in state S and took an action A, the probability with which you can go to state S prime is this. Okay, one of these terms. This is literally the expectation with some probability go to S prime, and at that S prime, you will take some action A prime. And if you take that action A prime, there is some actual state, this action value function evaluated in that pair. Okay, so this explicit expression is showing you how a state action pair is related to other state action pairs. Similarly, for the previous equation, without the action step, you can write how the value of the state is related to values of other state, without the randomness, because you can explicitly write, you can drop this and say P of S to S prime, what is the probability? P of S to S double prime, what's the probability? Okay. So that's expectation equation, and this is the last slide before I talk about the solution, which is Q learning. Because I'll skip a couple of slides which are something else. But first, let me mention what now that we have kind of related value functions to the model, now we want to relate it to policies as well. Okay, and in fact, let's not just relate a generic value function to a policy. We'll actually directly talk about what is the optimal policy and how is it related to the optimal value function. Here's the thing, right? So the optimal state value function, V star, is the maximum value function over all policies. So if I have V phi of S, okay, it's one number, right? Remember, for every policy, given a starting state, there's only one number. Right? Remember, this is the expectation of all the rewards I can collect under that policy from that state, right? So if I maximize over all policies, let's say if I have like 100 policies, okay, one of those policies will lead to the highest number, right? I mean, or maybe there could be more than one, but let's say one of these policies is leading the highest number, then whatever the highest number is, let's call it the optimal state value. Okay, so V star of S is the optimal state value function. It's just the highest of all policies which can give high value to that state. Okay, similarly, the optimal action value function is going to be very similar. It's just given state, given action. There are many policies following that that give a number to this. Which policy led to the highest number? That's the Q star of S comma N. Okay, right. So you still have the three degrees of freedom, which is what is the starting state, what is the action. But given these two, there's going to be one of these policies that led to the highest value. Right. So that we're just looking at those values. Okay. So the objective for Markov addition process is to really find V star of S and Q star of S comma A from some starting state or from some starting state action pair. That's all it is. So the objective of planning problem is, if you know the model, like the script piece and script task, which you just saw in the previous slide, how they're related to the value functions. If you know the model, you just want to find the optimal value function or the optimal state action value function. Okay. Why do we care about this and not the expected sum of rewards? Because value function is actually the expected sum of rewards, starting from some starting state. Okay. Remember, we said at the beginning, what is the RL objective? What's the planning objective? Is to find the actions which maximize the expected sum of rewards. But finding the actions that maximize the expected sum of rewards is the same as saying find the policy which maximizes the expected sum of rewards. Okay. But if you maximize the expected sum of rewards under policies, this is what you get. V star of S from some starting state. Like let's say the class 1 or something, some starting state. Okay. So therefore the planning objective at least is clear, that V star of S. Okay. Even for RL objective is still the same. I mean, we have to maximize the sum of rewards by taking actions. It's just as an extra trail and error exploitation, bandit feedback aspect there. But we still have to maximize this. And this is very similar to each other. What's the difference between this and this is when you take A to be the optimal action. Okay, optimal policies action here in the first step also, then this is going to be the same as that. Okay, but let me sorry. It turns out, and this is going to be something we will not discuss in this class. Okay, Bellman expectation equation was intuitively understood as how we can get to expectation equation, because we just said, okay, linearity of expectation value at a state is related to value of other states under a policy. Okay, we have another set of more another set of key results which are called Bellman optimality equation. Okay, which relate the optimal value functions or the optimal state action value functions with each other. Okay. This is the optimal state value function just from the previous slide. This guy is related to optimal state action value function at other state action pairs. Okay. This we're going to just take it as granted. We're not going to derive it in this class, but this equation is called a Bellman optimality equation. Okay. Why optimality equation? Because it's relating optimal state action value function here. Or you could also actually the same type of equation can be written for V star of S also, but I didn't write it here. Okay. So this is called the optimality equation, and if there was pi here instead of stars, okay, then it would be called expectation equation, but there would not be this extra max. Just to kind of, if you want to kind of differentiate between what was the previous equation, what is this equation, if not with this, the stars would be pi's. That's it. Okay. This actually Bellman optimality equation is actually the underlying idea behind dynamic programming in computer science. You know, so if you have ever done interviews related to if there's dynamic programming questions being asked, I know some people try to apply to data engineering or some of the more little bit software engineering type of roles, they might ask programming questions, and so dynamic programming is related to this equation, literally Bellman optimality equation. Okay. But what I want to say is that if you look at this equation, okay, this equation is saying, as long as you tell me the model, like let's focus on planning. As long as you tell me the model, okay, I know that optimal state action value function at a pair is related to state optimal state action value function at some other pair. Okay, I can write this equation for many pairs, right? So I can write the same equation for S comma A, S prime A prime, S double prime A double prime, and so on. So many such equations. So this is going to be leading us to a system of nonlinear equations. Okay. Why nonlinear? Because there's an extra max. Okay. You know, if there was no max, it would be a linear equation. Linear in what? Linear in the Q star guides. Q star of a state action pair is something that we don't know. So this Q star, just think of this as like x1, x2, and so on. So these are unknowns. Okay, we don't know it, but we know that those unknowns satisfy a nonlinear equation, and you can write this nonlinear equation multiple times. So you can have a system of nonlinear equations where there's unknowns. Okay, these unknowns, because this is, let's say we are planning situations, so we know these. Okay. So you have a system of nonlinear equations, bunch of unknowns. If you can somehow solve it, very similar to system of linear equations, you can solve a bunch of, if you have unknowns, you can just solve it using, if ax is equal to b, then x is equal to a inverse of b, right? So you can just solve it, right? System of linear equations. So very similarly, a system of nonlinear equations also you can solve it. Okay, to solve it, you can actually get the q star of s comma a, right? So you can actually solve for the optimal solution. Okay, optimal value state action value function by just solving the system of nonlinear equations. Okay? And there's people do that. And once you solve it somehow, here I just wanted to point out that there's one way to solve it. There are many ways to get to q star, but here's just one way to do it. But once you get q star, you can actually relate it to the policy as well. Okay, so that's why I didn't want to focus on v stars but q stars, because there's a very easy way to talk about policy. And this is the last connection. We connected model to q's value functions because value functions are related to each other through the model p's and r's, right? And now the optimal value function is related to the optimal policy in this way. If you know the optimal value function, because the second argument is free, you take the, you plug in every action and look at the action that is leading to the maximum value. Okay, and for that action which is leading to the maximum value is the action you want to take. Okay, so it's a very simple. I know it's like written in a very elaborate way, but that's because we want to make the distribution. We want to write it as a distribution over actions. So all it's saying is, if you think of the optimal policy, which is a distribution over action, that distribution gives zero weight to every other action except for the action except for the interesting action, it gives 100% weight, as in like its probability is 1. What action is that? Action which maximizes the Q star of S comma A over all actions. So let's say there are 3 actions, then you will compute Q star of S comma first action, Q star of S comma second action, use Q star of S comma third action, and whichever number is higher, that's my optimal action. Okay. So now we've related the policy to the value function also. So now I hope it's a little bit kind of reasonable to appreciate why we were studying value functions, because they're like, something auxiliary, right? They're not directly talking about policies, right? But if you could solve this, and we just gave an example of how to solve this, if you could just solve the system of nonlinear equations, you could get this. If you get this, then you know what to do in every situation. Okay, that's what you can do, and that would be the right, that would be one example of how to do planning. Okay, but we are not in planning; we are in a harder situation. We have to do exploration and exploitation, and learn over time. Okay, learn the model, for example, and things like that. So there's, we have to do a lot more effort. But if we knew the model, if we just solve the system of nonlinear equations, then we would just know how to take the best action in every situation. Okay, and these actions are already taking into account this trade-off. If I do something, I can be strategic. I can be doing some actions now so that I can reap higher rewards later. All that is captured in this, okay, because it's captured in the value functions. Okay, because value functions are looking at long-term rewards, not just the immediate reward that you can reap, but in the collection of rewards you can reap. Okay. So that's the solution for the optimal. So that's the solution if you know the MDP, as in if you know the model, and therefore you're just in planning. But what's the solution for our reinforcement learning setting? Okay, for that, just like the Bellman optimality equation, where we did not discuss how that was derived. I mean, we just assume that it's a fact. Okay. Similarly, we're gonna do that for reinforcement learning as well. So okay, let me skip that. Okay. I mean, there was only one slide we skipped. I mean, after questions, I mean, there's questions. I'm going to talk about now the one solution strategy for which I needed the value function, and that's why we introduced the Q of S comma A, because I wanted to kind of, what is the Q here? Q stands for the state action value function. Okay. This slide is just trying to say that you have to do exploitation. I mean, we are not in a planning situation. We don't know the model, so we have to do both. Predict how my current policy is going to perform, and also control that and change my, make an improvement from policy to policy. So in the sense that as I'm interacting with the environment, I may have a best guess of, oh, this policy is good, but I need to do explore and exploit so that I can improve my policy. Like improve my policy means take better and better actions in the future, right? So that, one way to kind of broadly categorize it is to call one of these stages, or one aspect of this problem called prediction. The other aspect called control. Prediction means for a given policy, I need to have a good estimate of how it's performing. And if I have a given policy, how do I improve it a little bit? Okay? That's how you would think about any solution strategy in this RL problem. Generally, you kind of want to know how you're doing at least each of these aspects. Okay? But that's just at a more higher level. So let's actually really look at one algorithm and stop there. How do we derive this algorithm? Just like all the other previous strategies, right? UCB or epsilon greedy, we are not doing anything from first principles. We're just saying this is the strategy or algorithm, and that's it. Okay. We just we have some intuition of why this algorithm may make sense, and in fact that's why we spent so much effort in defining value functions and Bellman expectation equations and all that, just so that it kind of helps with understanding it. So okay. So how does this algorithm work? So algorithm just means a sequence of steps. Basically, in our online machine learning loop, right? Basically, in our loop where the agent interacts with the environment, takes actions, gets the next state and the reward. That's a loop, right? So we start with an object, which is just a table, okay, which is just a matrix, a table or a matrix. Okay, the matrix is of size number of states times number of actions. Okay. Right here, this is one of the reasons why it's not scalable. Okay, you're not going to enumerate all the states that are possible. You cannot enumerate all the screens that can appear, or all the camera input images cannot be enumerable, right? but we'll fix that next time. So you create first a table with number of states times number of actions. Okay, so it's a matrix. Start with some starting state, let's say S1. For every time step, you do the interaction, right? So what is the interaction? Take an action. Take an action. But how do you take that action? It's exactly very similar to the epsilon greedy process. With some probability, take a random action. Okay, this is why last lecture, the first algorithm is solved with epsilon greedy. With some probability, take a random action. Okay, in the multi-arm managed setting, right? Okay, that part is exploration. With the remaining probability, you take the action that maximizes the Q value in that given state. Okay, what is this Q value? This capital Q value is this initialized matrix. So let's say you put random numbers in there, it's totally fine. So you pick some Q value. Pick the action that maximizes Q value across your action. Okay, and you play that, or you take that decision with with the remaining probability 1 minus x. Okay, so this okay, why are we doing this? It's exactly, remember we just saw in the previous slide that if you knew the Q star, then this is the right thing to do. Right? If you knew the best or the optimal state action value function, then you taking the R max over the second argument is going to give you the right action take now. Okay, so in the best, if you knew in hindsight what the Q values were, this is the right thing to do, but you don't know. So a little bit of the time you have to do exploration so that you can hopefully get some feedback so that you can update these guys, and so therefore you can better and better hopefully over time this capital Q matrix starts having entries of the cell equal to Q star or as close to Q star as possible. Okay? That's the idea, right? So you have to do exploration because we are in RL setting, not planning setting. We don't know the model of the environment. Okay, still we want to kind of get this table of Q values to be as close to Q stars in the cells as possible. That's what we want to do. And for that, the only, I guess, key step remaining that I've not told you is how do we update this Q given the feedback. Okay, so what is the feedback? There's some R value that we get. Okay, somehow with that R value, I will have to update entries, some entry in this Q matrix. Okay, with that I'm done, right? So every interaction, I take some action, I get some reward value, I have to update this matrix, something in that matrix. Okay, and I am taking care of exploration, so I'm not missing out on what would have happened if in that state I took some other value. I'll still get a sense of it. Okay, so this doesn't make sense for situations where you can't take multiple, you don't revisit the state enough number of times. So you have to come back to the states and try something else. Otherwise, you don't know what the best thing to do in those states is. Okay, so what is that update? Okay, now this update is gonna, we're gonna intuit it by again referring back to the Bellman optimality equation. Okay, so what is the update? It's just saying, okay, only update one entry. Okay, only update one entry in this Q matrix. Remember, Q matrix has states times actions. So one of those entries corresponds to, in the state, what action did I take? That only corresponds to one of the states, one of these cells in that matrix, right? So in that matrix, I'm only going to update that cell. How am I going to update it? The old value plus some alpha, which is like a learning rate. So think of alpha as 0.5 if you want. Okay, some constant, okay, alpha t if you want to, for now. So some alpha times the difference between two entries. Okay, difference between two values. The value on the left hand side actually includes the feedback that I get. Okay, this is the only place where I got the feedback. This is RT plus 1. Okay, and this max of Q of S t plus 1 comma A is something that I can compute. Sorry, I get the feedback and I also know what the next state is. Okay? I mean, that's what the environment will tell you. Here's what the next state is. Here's the reward. And so I use the reward, and at the next state, I'll take the max of all the, under all the actions, what is the maximum Q value I can get? That's this first two entries. I'll subtract the current Q value. Okay, this difference is called the temporal difference error. Okay? So all I'm saying is, whatever the previous value is, I'm going to have this what is called adjustment or some error. And in the literature, it's called temporal difference error, but you can just think of it as some adjustment, some weighted adjustment. I'm going to add this weighted adjustment to the old value to get the new value. Okay. So I'm updating one cell after one interaction, and the new value is nothing but the old value plus some adjustment. Okay. In fact, another way to look at this is just remember, so you can see that the first term is the same as the last term with the alpha in the front. Okay, so you can just think of it as the new value is just 1 minus alpha times old value plus alpha times some new information. Like if you want to bring this to the, merge it with this, it's nothing but new value is 1 minus alpha times old value plus alpha times some new information. Okay, now this new information, is just in terms of intuition, it's just very crude, but you can go back to that expression. It looks very similar to this here. Okay, it's like some RT plus 1 plus max. I mean, since there's only one interaction, so one sample, so it's just RT plus 1 plus gamma times max of the next value, the new state that I'm in, and what is the max over that. Okay, so there's some inspiration of this Bellman optimality equation in that expression. Yeah, this expression. I mean, it's similar. I mean, I'm not saying it, exactly follows from there from the first principles, but it's similar. Okay, so RT plus 1 plus gamma max of some Q. Okay, we don't have access to Q stars again. Some difference, but this is it. This is the update. Okay. Now this algorithm is what back that what is it called? Flappy Bird. Yeah, Flappy Bird example that we saw earlier. This is what they're doing. Okay. Just this code. This seems this code is not hard, right? So in the Flappy Bird case, in fact, they're not taking the screen as the input, just the coordinates of the bird and the location of the pipes, and that's so discretized. So within is the coordinates like 1, 1 or 2, 2, something like that. Okay. So they're only finite values for the state. Okay. So what is very similar to epsilon greedy. Epsilon is the exploration parameter, and alpha is very similar to something called a learning rate. Okay. We've seen learning rates before. Interestingly, long time ago, I don't know how many years ago, 30 years ago, this under some assumptions, you can show that after a long enough number of interactions, this Q matrix is actually the matrix of the optimal state action value functions. So state action values. Okay. And this was shown like a lot of decades ago, right? I mean, so this is very interesting as well. So this is an algorithm just doing some exploitation and just getting some feedback and doing some update. And it turns out after long enough time, every entry in this matrix is actually the Q star of S, okay. That's a very strong support for why run this type of an approach. Okay. So that's the Q-learning algorithm. Let me just I don't think I want to talk about any of this stuff today. Yeah. So actually, any questions before that with the Q-learning algorithm? So I'll start with the Q-learning algorithm next lecture, but just again, just the algorithm description as just one page, right? And then we'll talk about how to scale it up. Okay, that's where deep learning will come back, and that's the last kind of tying back deep learning with decision making. Okay, that's the goal for this next lecture. Okay, any questions about the current all that? Just the algorithm. Like what's happening in terms of action selection. You start with some random numbers, which is of this size. Take actions with some randomness, either with some probability take a random action, or with some probability take a kind of the current best action that you can take. Okay. And every time you take that action, you get a next state and a reward. Next state and the reward are part of this, these two terms. And you can do a moving average basically 1 minus alpha times old value plus alpha times this new value, or you can look at it as old value plus alpha times what is called a temporal difference error. Okay. So That's it. That's so this other than the update equation, the rest of this stuff is kind of clear because it's just epsilon greedy. The update stuff is doing something magical, and that's why you're getting great. Somebody showed that the researchers showed that you can actually get to Q star of S comma A by just doing this exploitation in this way. Okay. Obviously, there's some assumptions involved here, and I will not get into that detail. And you can go to this paper and look at it. And the implementations are available online. Next time I'll show in code the same equation, and we'll see how it's how it runs. Okay. Maybe I'll update the repository with the code also beforehand, but we'll see a simple demo, and then we'll look at deep learning part. Okay, thank you.